Hello, everyone. Good evening. Great to see you. Thank you for joining us. Welcome to the end of part one of Programming for Lovers and one of my favorite sessions of the course. I thought how we'd start tonight, given that this is our sort of the halfway, we're going to be at the halfway point of what we want to build with our main course, is maybe for you to have the opportunity to reflect a little bit on what you've learned in part one. So tell me what are the big picture major learning objectives that you feel like as the result of going through part one, we've come across. And certainly we could name, I always say to students, we can name individual things, right? We can talk about what we learned about, two-dimensional lists and things like that. But I always say, can we zoom out a little bit and go a little bit more meta and identify things that are big picture, things that maybe you didn't know or appreciate about programming that now you do, especially things that may have been recurrent themes that we've seen as we've gone through the first part of this course. What would you say? And also, I think it's an opportunity to say, secondarily, how do you feel about where you are now versus where you are when you started? Whatever that difference is. How do you feel about that? So this module is all about top-down programming, and why we do that is because the projects that we work on in this chapter are larger than what we've seen before. And so we can't just put everything into main. A lot of times when folks learn Python, one of the nice things about Python and something that we haven't seen, you don't even need a def main. You can just fire up a Python file and just start typing code into it and then just run it. But the problem with that is that that's not really scalable. So as soon as we need a larger programming project, life is not all about just setting a variable equal to something and then calling, doing something with the variables that you've set. We need to do these more complicated tasks of reading in from a file and passing this into a larger engine of code and doing visualizations. And when you move program towards larger projects like that, then you have to see all this structure, and how we structure it is very heavily top-down, absolutely. And so delegating the subroutines and laziness, I think, is a virtue in what we've seen. Excellent. Yeah, and John, if you like structured procrastination, today's going to be all about structured procrastination. Good answer, of course. You probably know a lot more about Python syntax. Fair enough. Absolutely. Another good point, programming is really, as much as anything, it's a way of thinking. That's good. And if you like that, like if you feel similarly, I think that's a fantastic sales pitch for the second part of the course, where that will become even stronger. So so much of what we're going to do in the second part of the course is to think about how it is that we think about things, how it is that the programming language might think about things, and what's going on really inside of the computer, and how can we think like a computer. In an era of AI, when AI can write code, this is still an extremely valuable skill to have, to think like a computer and to frame problems in ways that computers can solve it. So good. We saw a lot of visualizations, sure. And writing simple functions rather than relying on Python-specific things. I like that. I think at the start, we probably overdo it a little bit. Like, is there really a need to write a min function? I don't know, but one of the reasons why I wanted to profile is to show you that these things probably are optimized by the programming language, but there's no mystery in what a lot of the built-in functions do for us, right? And so even though it's nice to have a lot of built-in functions, it's kind of ironic because when you're teaching somebody for the first time, a lot of these built-in functions are the natural sort of examples as to what you'd want to teach. So it's, as we move up levels, what we're going to see is it's fine to have these sort of abstractions and use built-in functions where appropriate, especially now that we appreciate how they work. All right, and one other good point, thinking in terms of pseudocode and ideas and what we want to achieve before we write the code. I love that. So absolutely, that's right. And that's why, I mean, I don't know of another introduction to programming that covers it in the way that we do, in the sense of you don't have to come at the course this way, but I always suggest if you read the material, you have a very low stakes way of engaging with it initially. And then this gives you multiple contact points with the material. So I'm not worried about syntax. I'm unsticking the syntax of a specific language with what the idea is computationally that we're trying to express. So that's why I have the readings, and that's why we have pseudocode on our Programming for Lovers website, so that you have the opportunity to think through this and see it initially in a way that is unstuck from the syntax of any particular language. And one of the things I'm trying to convey is, so with that, so many learners say, I want to learn Python. And languages change and come and go, and that has been the case for a really long time. But there are some core tenets of programming, like modularization, that are not new and I don't think are going anywhere anytime soon. Great. Speaking of reading, I'll say, first off, notice I pinned the starter code for today. So you're going to see I've got my Cellular Automata folder. If you haven't had a chance to download that, put it into Python SRC, make sure to do so. And you can grab that from the link that's pinned, or it's on the associated code along page. But speaking of reading, that's a great plug for me to say. As a note, and I said this at the start of our last stream, we have our ebook accompanying the course now. So if you want to just, have some material that's on the go and give you a way of reading this, we've added 2 chapters accompanying the part 2 material. So I thought I'd show you, here's sort of what it looks like in Apple Books. This is the R Pentomino and our Gosper Glider from last time. And we have all the readings, but we also started adding a lot of the, for the first 4 chapters, we've got code alongs in there too. So you could read the code alongs as well. Like, here is what we're going to do in this current stream. So everything, if you haven't had a chance to take a look at this yet, it's got some really nice formatting to it, and I think it wound up looking really good. So this, if you are on our mailing list, I sent this around with a direct link to purchase it on Gumroad, and there's a promo code, I think, until Monday, or we give this away for free to all of our Phillip Math subscribers. So you can check it out there and get a copy of the book for free. And while I'm on sort of those sorts of updates, I wanted to show, we also have our projects, which are exciting. So for everybody, as you've gone through the first 4 chapters, it's great to have code alongs. It's great to have practice exercises. In our survey, what we found out, and what I've heard a lot from learners over the years, is how can I take the next steps, right? I've got this great foundation. What can I do now? And we put a post out about that as well today. But over the next few years, over the next several weeks, starting March 9th, we're going to have like a 6-week sprint. If you would like to complete a project, and we have a menu of 5 things that this message went out to our Phillip Math subscribers. So if you're a 6-month or annual subscriber, then you have the opportunity to sort of unlock our project. And we do that because we're going to have like frequent check-ins with our TA Anna, and you'll even have the opportunity to present your work at the end to me, which will be exciting. And we've picked some project ideas. There's one that's missing that I need to add here, which is the SIR model of epidemics. But all of these projects are like inspired by biology. And the other thing that's neat about them is that they are models. So there's two attributes that I like. Number one, they're models that come from real models that at one point in time were published research. And secondly, you can code all of these projects only using stuff that we have done up until this point in the course. So if you're interested in a deeper dive, we're going to have these like projects on Rails with opportunity to get a little bit of one-on-one feedback about your work. And that will start on March 9th. So part 2 is going to start on March 9th as well. So we'll have next week to kind of catch up and allow you to make sure that you're submitting your practice exercises, getting all on the same page, figuring out if you'd like to complete a project over the next several weeks. And then those will start March 9th. That's it for course announcements. We're going to start, and I'll put a link to that if you're interested in the chat. But we're going to finish up part 1 this evening, and then I get to relax finally for a little bit of time. But thank you for joining me for the first half of the course. It's been a privilege and a joy, and good job to everybody. So especially wherever you feel like you've gone from here to here in the course, whatever that progress has been, well done. And we're going to keep going. We're going to have a course in introductory computational biology going out this summer. Part 2 of the course is going to start after next week, and there's a lot more to do. So lots of fun to be had. Tonight we're going to take what we built previously with the game of life, and we're going to extend it to literally potentially an infinitude of cellular automata. So what we're going to do is not going to necessarily take an alive or a dead state. It's going to take an arbitrary collection of states, and then we can specify rules based off of neighbors however we want. And that might seem way harder than what we've done up until now. But it's what we're going to see is this idea, and one thing that I would say is a big picture learning objective that I hope we've seen is that if I can do something once, I can do it a bunch of times. And this is kind of the flavor of that, which is if I can do an example of something, in this case, the game of life, then I also can probably generalize that into code that will handle a larger family of cellular automata. So one of the things that I will say as we go through this, but I want you to pay attention to as we do, is that there are many opportunities to take code from the game of life and either make a very tiny change to it, or in some cases, like keep the exact same function. So the structure of the code that we're going to have is going to be very similar, and you'll have a chance to see that as we go. For now, though, that's plenty of intros. Let's keep up the good work in the chat. Let me know if you have questions as we go. This is, we're kind of picking up the challenge a little bit, and it just like what we've seen before at the start of part 2, we're going to go back to basics in terms of we'll work with object-oriented programming, but we're going to start at a pretty simple level and with some ideas that are going to be basically very similar to things that we've already done. So this is in the spirit of the treadmill. The treadmill will be quick today, and then when we go back and start part 2, we're going to slow it back down a little bit. But for now, I think we're ready to get started, so let's code. All right. To get started, we've got our starter code, which is a Cellular Automata folder that lives in our Python src directory. And it makes sense for me to walk through our directory structure a little bit. So we've got an intimidating number of initial boards in our boards folder. We have something called color maps that I'm also going to explain when we get to it. This is going to help me color different cells of the board with different colors as we go from just having alive and dead to having automata that have like multiple different states and that allow us to color each of those states with something different. So we'll see that in a second. Oh, there's a folder that only I have. It's going to have some images and some final videos that I can show you without having to run this automaton a lot. Output is empty. That's where we're going to put our visualizations. Rules are going to specify all the rules of the different automata that we could run. And then in terms of our code, animate.py is the exact same thing that we had in our game of life. So this is just going to have some code that's going to allow us to produce a video animating the results of what we see. And custom IO is going to have some code that's going to read some things from file. As we go through this, some of the things have already been provided for you because they're either identical to what we've done before, extremely similar to what we've done before, or maybe both, but also maybe a little boring too. So for input output, I'm not going to write a bunch of code to parse stuff from file because we did so much of that with Game of Life. There's going to be one new thing that we do, and so I'll show how that's going to apply, but as you're going to see, the code is going to be very similar to what we have done previously. We're going to have a drawing.py file, and that's going to allow us to draw our automata game boards. And we've got data types, which is going to store our data, how we represent the data. And then we've got functions, which is going to have the engine of our automaton. So for producing all of the generations of the automata over the number of generations that are specified, and then updating a single board and so forth. And then we have main.py where I've done the command line argument parsing for us already because we saw that with the Game of Life. And then when we already worked with that with the Game of Life, you can take what we've done and it's simply a matter of processing sys.argv of 1, 2, 3, and so on. And sometimes you need to convert them to an integer or whatever. That's not the most thrilling thing, frankly. And so I've given us that for free because it's so similar to what we've done with Game of Life. I'll point out one thing where we're going to change. And I'm going to represent a state of the board. Before we represented it as a Boolean value. So it's either alive or dead. And that's because this collection of states, each cell could be alive or dead. So there were only two possibilities. When you have two possibilities, there were Boolean values that you would use to represent it. And then how we're going to generalize this is to say, instead of a two-dimensional list of bools, we could do a collection of things. One thing we could do would be to use integers, and I think that's perfectly reasonable. What I'm going to do is I'm going to use strings for a technical reason when it comes to parsing in the rules. It doesn't really matter which direction we go. I like having strings because then I can think, well, I guess my states could be state could be apple or smiley or heart hands emoji, right? So it frees you from thinking about the states as numbers, and then the states are just these arbitrary names. So the game board, and this is the alias abstraction that we saw last time, I'm going to think about a game board as a two-dimensional list of strings. So every position of the board is just going to be a string corresponding to the state that it represents. I would like to start, though, with just implementing this. So let's do the fun part first. And then that will allow me to go through and quickly go through how the drawing is going to change, how the parsing is going to change, and so forth. So if I look at functions.py, I want to import my game board alias that I have in data types. And you'll see that I've written out, a high-level function for us. And I've got a bunch of functions in here. And I think by what you told me about the fact that we are looking at modularity and top-down programming as a learning objective, I don't even have to ask you where we're going to start. We're going to start at the highest level function. And this function is going to take our initial board. It's going to take the number of generations that we're going to run this for. It's going to take the neighborhood type. Now the neighborhood type here is going to be Moore or von Neumann. And we'll say a little bit more about that here shortly, but it basically depends on, am I including my diagonal neighbors when I consider the neighbors of a current cell? And it's going to take a collection of rules. So the rules are going to say, based off of my current state and the state of my neighbors, what do I update to in the next generation? So I'm going to represent the neighborhood of the current cell as a string, and the next state, or the state in the next generation, is going to be also a string. So that will be what I update to in the next generation. For now, I will just point out, you don't have to necessarily hold all of those abstractions in your brain simultaneously, because if I'm going to play an automaton, I'm going to take an opportunity to go back and look at the game of life and say, well, when we implemented the game of life and we programmed this top down, I thought we did. We had played game of life. We took an initial board, number of generations. We did some error checking, and then we said, the first thing that I want to do is simply create a list of game boards. And I also want to probably make sure that the initial board is indeed rectangular. But then I'm going to range over the number of generations, and then I'm simply going to update the current board and add that new board that I get to my collection of boards. And that's all I'm going to do, right? Laziness is indeed a virtue. And so my function is going to have that exact same structure. I might even consider copying it over, right? I think there are some things I probably should do, like I could copy all of this over, right? It's hard to imagine how anything here is going to change. So all of these initial checks are going to get copied over into functions.py in the automata folder, and that's where I'm going to start this. Okay. So I want to make sure that the board's a list, that it doesn't have 0 rows, that the number of elements in the first row isn't 0, and I want to assert that it's rectangular. So I'll call that helper function. But then all this function needs to do is to declare my boards and then range. So I'm going to say boards is equal to a list of game boards, and I know that behind the scenes that's a 3-dimensional list of strings, but it's also just a list of game boards, and it needs to start off as being empty, and I'm going to append to that the initial board that I have, because I know that it's not empty and I know it's rectangular. And then after I do that, I'll say, well, range over the number of generations and append the current generations board after updating. And here I'll say for I in range over the number of generations that I have. Well, the current board, or I'd say maybe the next board, is equal to, I'm going to call a subroutine update board, and I'm going to give it boards of I, which is the current generations board. And I also need to give it everything that is relevant, right, to the automaton that was passed in as a parameter to play automaton. So I've peeled away one parameter, but all the other parameters are going to get passed in the subroutine. So I need to know, is the neighborhood von Neumann or more? And I need to know what are the rules of the game, because now the rules of the game are going to vary depending on the automaton that we're implementing. For that reason, I'm just going to pass in the neighborhood type, and I'm also going to pass in the collection of rules that we have. So both of those things simply just get passed down into the update board function. And then after I've called update board, well, I just want to append the next board that I've obtained to that growing list. And then I want to return the boards. So that function again is short. Again, we see this principle. I can do something once, I can do it 1,000,000 times. So most of the difficulty is just in writing the function to update the board. And then we're going to iterate that idea. So when I look at the function for update board, we've got a current board, we have the neighborhood type and the rules, and we should perform some checks for this for sure. And I'll just say, I think I'm calling it initial board, but I'll copy down some of my parameter checks that I have here just to say, there's no harm in applying these same sorts of parameter checks, except I guess this needs to be current board And it's going to be hard for me to imagine how it's not going to be rectangular if I do this right, but there's nothing wrong with checking it. I don't need to check the numgens parameter because I've already checked it. It's not in this. And then I'm just going to change this to current board. And I'm going to change this to current board 2. So I have one more initial board. And then once I've done that, then I can go through the process of updating the board. So to do that, we're going to say this is identical to what we did with Game of Life. When I update the board for the Game of Life, well, I create a new board with the appropriate dimensions. So I'll say that the number of rows in this new board is counting the rows in the current board, and that the number of calls is equal to count the number of columns in the current board. And once I do each of those two things, I'm going to declare a new board based off of initializing it with the appropriate number of rows and columns. And way down here, that's eventually what I'm going to return. So I'm always thinking about in terms of inputs and outputs. What is it that this function returns? It returns a game board. And so as a result, that's what I should return. So I've done these three things. And then what we would like to do is iterate over all of the cells and pass our work to one of our minions. In that case, a subroutine. So this is the same structure we saw for Game of Life, where I can range over the number of rows, and I can range over the number of columns, and then I can say that the new board's element at position RC is equal to, let's call update cell as a subroutine, and I'm going to give it the current board, I'm going to give it RC, and I'm going to also give this function the neighborhood type as well as the rules. And so we're delaying, like this is, again, I think as John told us, it's structured procrastination, because I could write it in this way without even really knowing how either of these things is actually implemented. I just need to know, well, I might imagine there's different numbers of cells in my neighborhood that are going to contribute to this update, and the collection of rules for the game need to be specified, and I don't even necessarily know how they're specified yet, but I can still write the code in this way and everything will be good. And so, and notice this is the exact same structure that we had before. So I've passed the work of playing an automaton over many generations very quickly to the work of updating one cell of one automaton in one generation, because that's ultimately the only thing that we're doing. We're just applying it over a huge number of cells and then over a potentially huge number of generations, but nothing actually at the end of the day changes. So any time that you have that repeated idea, you can notice when you're building a project that even if this may seem complicated, I'm doing the same thing potentially billions of times, and so I just need to make sure that I'm implementing that one thing as a subroutine on its own. So then that makes it easy to debug and easy to check, because it would be hard for me to imagine how any of this code could really be wrong at this point in time. And so I've passed the work down to as simple of a subroutine as I can, and I'm going to carry on doing this. So before I do, I'll just say, yeah, well, what about, Philip, what about all these subroutines? And here's an opportunity for me to say, assert rectangular is the exact same subroutine that we saw when we implemented the game of life. Counting the number of rows in a two-dimensional list, well, that hasn't changed a whole lot. And the same thing for the number of columns and initializing the board. The only thing that needs to change about initialize the board is that the game board is now a two-dimensional list of strings, not bools. And so when you look down here at the bottom, you'll note count rows is the same. It just returns length of board. Count calls is going to make sure that the board is rectangular and then return the number of elements in the initial row. And assert rectangular checks the length of the first row and then ranges over the rows and makes sure that every row has length equal to the first row. So this is the exact same function that we saw before when we implemented Game of Life. So all those helper functions are done, which is great. And this shows us, once again, the beauty of modularity. Imagine that you had 250 lines of the Game of Life engine, which is what we had before, but you hadn't written it as subroutines. Well, then you're going to have to go through and manually inspect line by line and say, is this relevant? Is this relevant? What a nightmare that would be. Whereas now when I have subroutines, 4 of them basically just get converted over. And I guess I have the initialize board function too, which is here somewhere. Yeah. So I have initialize board. And instead of it, it's the same code as what we had with Game of Life. I declare a blank list, blank game board, and then I range over the rows, and I create a row that's equal to a bunch of default values times the number of columns. So each row spans the number of columns, and then I append each row to the board as I go. Before, this default value was false, and now what I'm going to give it is a default value equal to a state, which is the string 0. So if I were using integers, I would probably just have a 0 here. I'm going to treat my default state as the string 0. So note that just because, as I said, the game board is a 2-dimensional list of strings. With that done, we can now update a single cell. And so when we update a single cell, we know we're going to take the current board. We're going to take the row and column indices that we care about. We're going to take, how many neighbors am I considering? And we're going to take the set of rules of the game. And I've got a little bug here. This should be a string. So we need to specify that we're returning the state of the cell at this row and column in the next generation. And it's at this point that I probably need to understand the rules. I can't update a cell of a cellular automaton if I don't know the rules, right? And it would be hard for me to imagine how I would write this function. I've delayed having to do something hard for as much as I can, and I'm going to try to still do it. But we should know a little bit first about 2 things, the neighborhood types, and then how is it that these rule sets are actually specified. So first off, let's look at, and here's where I'm going to go into my other folder and say, we could look at, for example, Moore and von Neumann. So von Neumann is the godfather of cellular automata and the person who first worked with them and was interested in the concept of coming up with a system that could self-replicate. He actually formed a self-replicating cellular automaton, although one that is not as beautiful or simple as what we're going to see later on. The automata that he was interested in, and the one that exhibits self-replication that I will show you, considers the neighborhood of a cell when it's performing updates for the next generation. It says I'm looking at 4 cells. I'm looking at the thing north, east, south, and west of me. So what are the cells that are my directly adjacent neighbors? We also have a Moore neighborhood, though, which is what we saw when we worked with the Game of Life, which is that we also include these diagonal neighbors when we're considering what constitutes the neighborhood of a given cell. Once I know that, I will specify that the neighborhood type is either going to be von Neumann or it's going to be Moore. And you might imagine, I don't know, maybe we're going to extend this to have cellular automata on honeycomb hexagonic lattices, in which case we're going to have 6 neighbors. And there's all different possibilities that you could imagine here, but I'm going to consider just having 4 neighbors or 8. Those are the simplest types. And then I also need to take a quick look at rules. So if I look at rules, let me examine, for example, the Game of Life rules. And in this case, and I've just noticed my starter code has this written out, not in snake case. I'm just going to change that to GOL_rules. But you look at the rules of this game and you say, what does this mean? And I could look at the Langton loop. And what does this mean? So we have a string of some length, and then we have a colon, and then we have another element. And in this case, everything here is represented as integers. So these are 0s and 1s. And in the case of the Langton loops, we have more numbers. So you have a 5 or 6 or a 7. And we'll work with processing that a bit more. But for now, I did want to show you how it is that we could encode, like what is this exactly encoding? So the start here indicates the value of the current cell, followed by its 4 von Neumann neighbors, followed by whatever the state of that cell needs to be in the next generation. And for the game of life, you have longer rows because you have more neighbors. So for the game of life, if we look at what we have, our rules were the current state, and then these are the states of its 8 neighbors, and then that's the next generation's state for my current cell. So we need to understand how is the order here of all these neighbors getting represented. And if we look at, here's an example of arpentomino. This is the arpentomino that we worked with Game of Life, and I'm going to consider the central square of the arpentomino and say, well, it has a certain value, and now I'm going to view 1 as alive and 0 as dead. Its value is 1 in this generation, and so if I look at its neighbors, I need to agree upon how I represent the neighbors. So I'm going to say, let's start in the northwest corner, or top left corner, and I'm just going to read out clockwise. So this rule would be represented as, the neighborhood, I should say, is represented as 1, meaning I am alive, and my neighbors are 0, 1, 1, 0, 0, 1, 0, 1. So I can probably find this rule if I write it out and say 1, 0, 1, 1, 0, 0, etc. Or I could look at similar rules, but if I look at, where do I find anything that's 1, 0, 1, 1, here's a similar type of rule for this, or similar type of pattern or neighborhood, I should say, for the game of life, which is that my central square is a 1, my top left square is a 0, and then I move clockwise around and hit 1, 1, 0, 0, 0, 0, 0. And I say, if I see that particular configuration where I'm alive and my neighbors look like that, then in the next generation, I'm going to be alive again. So I'm going to specify that that's a 1. And the idea is this is a long file to try and specify, a number of different alternatives here. And there's also, we have rules for the Langton loop, where we have a von Neumann neighborhood. The von Neumann neighborhood is simpler because you have only 4 elements. So the neighborhood is represented as 5 elements. And so if I look at I think I've got Langton neighbors here. So let's say, for example, I have a central square and it has state 1. And now 1 is no longer necessarily alive, it's state 1. And in this particular case, just the way that I'm going to view this is to say, if I'm state 1, and then I look north, east, south, and west, so I'm going to go top and then clockwise again, this neighborhood is represented as 12725. 12725. And when I look at the Langton loop rules, I'm going to say, is there a 12725? I hope so. Good. So this says, if you happen to see a 1 and then it's 2725, this tells me that in the next generation, this cell should get state 5. One thing you might wonder, I should say, is where's 12724? And the answer is we're going to form a very specific pattern for Langton loops, and that rule doesn't need to be specified because it's never actually going to arise. So there's a huge number of possible rules here for this automaton, and it turns out for what we want to implement, we're not going to need all those other ones that are not going to come up. So, and I should say I've even got another picture here. This is saying 12725 means that in the next generation, I don't know what these other cells are going to be because they're going to be based on their own updates. So this cell will be based off of 7 and then whatever is around it and then 1. But I do know that this cell that is currently having state 1 is going to get updated to 5. So this is represented by this rule string that we saw before, 12725:5, saying cell 1 is equal to 5 in the next generation. So that's nice, and this is something that we do a lot in computational science. Is we have an idea. How do we represent that idea like with a string? And in this particular case, that string that we're working with is just what we said, 12725:5. That represents a rule. So my idea then is that to update a cell, I'm going to convert the neighborhood that I see around me to this, and then I want to look it up in the file, or in what winds up this being represented as is just a dictionary. This is a string, and this is a string. So I'm going to take my neighborhood and say, what's the string represented by my neighborhood? And then look in the dictionary and say, is that a key of the dictionary? And if so, what's the associated value? So now I have this idea. I just need to convert it over into my function. And what we'll do is say, to update the cell, well, the first thing that I want to do is to convert this collection of neighbors into a string representing the neighborhood. Neighborhood. In the way that I've just said. So I'm a 1, and then above me is a 2, and to the left of me is a 7, and 2, and 5, and so on. So I want to take that neighborhood, I should say, myself and my neighbors, into a string representing our states. And by that I mean convert game board of RC. And here's our first point where we say, that seems hard. And so what does that mean? If that's hard, what is it that we should do? I was going to say run shrieking in fear, but the chat wants a subroutine, so that's what we're going to do. And here's where we're going to say, I'm going to take my current state, and I'm going to look at my neighbors, and I'm going to convert it to a string, which means at the end of the day, I'm going to represent that string just by saying neighborhood. Neighborhood is going to be represented as a string. And then I'll call a subroutine. You probably could have guessed because it's just lurking down there at the bottom. I'm going to have a subroutine called neighborhood to string. And it's going to take everything that it needs. So it's going to need board. It's going to need R. It's going to need C. It's going to need the neighborhood type. I mean, I'm truly being lazy. And it's not going to need the rules. So in the spirit of peeling away one parameter at a time and saying, it's going to need all of this. It actually is not going to need the rules, because as soon as I have the neighborhood as a string, going back to saying for my previous example, what I was showing with the visualization, if I've got this, I'm going to represent this circumstance just as 12725. And that's the only thing that this is going to do. That the subroutine does nothing apart from that. Once it does that, then I'm going to assume that I have it. So I'm going to assume that I have my helper has told me 12725. Okay, great. So I've got that string. And then when I come back into functions, I'm going to be able to say, all right, well, how is it that I'm representing the rules? You remember, the rules contain keys that are neighborhood strings and values that represent the state of the central square in the next generation. Let's say central cell of that neighborhood in the next generation. So if my helper helps me out by converting this neighborhood to a string, I'm basically good. I'm just going to say, well, first off, is the current string a key? And here's where we get to go back and work with our introduction to dictionaries and say, I know how to check that. Is it the case that neighborhood is in the rules? So if it is a key, great. I just need to look up the value, because that tells me what I want to update the cell to in the next generation. And well, I said this dictionary maps neighborhoods to whatever the value is in the next generation. Again, if you want me to refresh your memory, when we look at the Langton loop rules, we said if this is the neighborhood string, that central cell is getting a value of 5 in the next generation. And so this representation makes it really easy for me to determine what the next generation should be. It's just to say return, looking up in the rules of this neighborhood string. And that's all. And you'd say, well, maybe there should be, what happens if it's not in the rules? So we could have an else, although we've returned in the if block, so I don't need an else. I'm just going to say, if we make it here, what happened? Well, we couldn't find a matching rule. So let's give it a default state. And so at this point in time, I'm going to return the string 0. And I could say, or we could have a dedicated default. But I'm thinking about the string 0 as representing like a default dead state. So that's what I'm going to represent it as. So I've done something that's kind of a little clever, which is that I had 1, 2, 3, 4, 5 parameters here. And I've already processed the rules. So I've gotten rid of that one parameter. And now I've taken the notion of updating the cell, and I've said, I've handled the update. The only thing that I have to do is convert the neighborhood of a certain cell, whether it's von Neumann or more, to a string. So let's write the function that does that. It takes the current board, it takes an R and a C, and it takes the neighborhood type, and that's going to either be more or von Neumann. And then it's going to represent this string. It's important that we know the neighborhood type, because if I have von Neumann, it's going to be a 5-element string. And if it's more, well, it's going to have 9, because I have myself and then my 8 neighbors. So we should implement this function. And to implement this function, here's where the nitty-gritty is going to live, right? We've procrastinated the hard parts as much as we possibly can, I think. And here's where we should start. So the first thing I would say is, what's the easiest thing we could do? I know something about this neighborhood string of me. So if I look at, again, I look at something like this, or I look at my image, and I know that this string or this neighborhood corresponds to 1, 2, 7, 2, 5. Whether I'm working with Langton, or von Neumann neighborhoods, I should say, or I'm working with more neighborhoods where we have the central square followed by this. So that representation is going to be different, but there's going to be something that's shared across those two things. And what is shared? Whether I'm looking at a more neighborhood or I'm looking at a von Neumann neighborhood. When I convert each of these things to a string, there's one thing that's always going to be the same. What is that? Quick answer from BZ, good. All right, I like it. So in either case, we're always going to have the same central element. That's always going to be included, and it's always going to be first. So I'm going to start my neighborhood to include only the middle cell. And what's that? That's current board. of R and C. And you might think, well, also the adjacent neighbors are going to be there too. That's true, but remember that strings are what the fancy word for strings are, which is immutable. And so if I were to try and do this by adding just my adjacent neighbors and then try to get the diagonal neighbors in later, this is going to be a mess. So I'm going to probably branch instead. But what I do know is that the neighborhood string is going to start off being equal to the current board of RC, which is a string, so far so good. And then way down here, that's what I'm going to return. And then in the meantime, I want to branch based on whether this is a von Neumann neighborhood or more, and add, so concatenate on additional elements. And they've got to be in that specific order because the order matters. So it didn't matter for the game of life. You might be sitting there wondering, why did the game of life? And all I needed to care about was the number of neighbors that were alive. Great. But when we generalize automata, that's not necessarily going to be true. And so as a result, for like the von Neumann neighborhood and for, as well as for Langton loops, which we're going to look at, if I were to take 1, 2, 7, 2, 5, I could move this 5 over here and switch it with the 2, and I might wind up with I'm going to have a different neighborhood, and I might wind up with a different update in the next generation. So here's where everything just gets a little bit more general. And what's cool is that we're still going to be able to represent this with not that much code. So what I will do is I'll initialize a collection of tuples to represent the cells that get added to the neighborhood. Okay, so I'll start off with just, I'm going to call this neighbors. Neighbor cells, okay? And that's just going to be an empty list. And then I will branch based off of the type, and I want to say, what are these? So here's an opportunity for me to ask you, if the neighborhood type is equal to von Neumann, then in this particular case, I need to say, what are the neighbor cells? Okay, I'm going to update the neighboring cells to be equal to something. And the question then is, what are they? And you'll notice I'm doing something important, which is that I'm not converting to strings yet. I just want you to tell me what the cells are. And if it's helpful, remember von Neumann. If we look at our neighborhood, and we need to make sure the order is there. But remember that for the Langton neighborhood, we said we've got the center square, then we go up, east, southwest. And that's just a convention that I thought made sense, but you could pick a different one as long as you're consistent. So what are the cells? Good answers. I want to add a 1 to, or subtract a 1 from each of the row or the column, but not both. So that's a good pattern. And then I want to be careful that I do this in a way that makes sure I go north, east, south, west. So when I look at my picture, where's my picture again? Look at my picture. I want to go up first. So this is the same column but the previous row. This is the same row but the next column. This is the next row in the same column. And this is the previous column in the same row. Roy had a great observation, which is, you might be wondering, if you watched the Game of Life code along that we did, you might be confused because it seems like I'm being very hypocritical. It seems like I'm saying it's okay to like add, duplicate data. And one of the things I said with Game of Life is, don't like create a new data set when you already have a data set. And that's a good point. And that's why I don't want to create a new data set. I want to create a reference to the data set that I have currently. So that's like a technical point, but I don't want to go in and grab individual cells necessarily. What I'm going to do is I'm going to identify ordered pairs that correspond to the elements that I care about. And there's two ways of doing that. I could say go up a row, meaning like -1, but stay in the same column. And then I want to go east. So when I go east, I want to say I'm in the same row, but I'm in the next column. I want to go south, which is in one additional row and the same column. And I want to go west, and west is going to be the same row and the previous column. That's fine. And then I would need to add the x values into R and the y values into C, and that's great. I'm going to do something very slightly different, which is I'm just going to store the row and column indices that I care about, which are going to be R-1, and then this is going to be C, because this is the previous row, current column. This one is the current row and the next column. That's the east value. The south value is the next row and the current column, and the west value is the current row and the previous column. So those become our neighbor cells. And you notice I didn't create anything new here. I kind of did a little bit, but this is just helping me know like the coordinates that I care about. And I'll say else if the neighborhood type is equal to more, then the neighbor cells need to be something else. And then we're going to have an else. Whoops. We're going to have an else down here. And this else is probably going to raise a value error or give some kind of message. Invalid neighborhood type. Okay. And notice that check only happens in this one particular case. So maybe we could check it elsewhere with some kind of an assertion. But in the meantime, I'm going to say if it is a more neighborhood, here's a little bit of a trickier one, which is what do the neighborhood cells ordered pairs need to be, given that I've already entered my central square. And remember, this time I need to look at the northwest value first, and then north, then northeast, then east, southeast, south, southwest, and west. So how is it that I represent these? What are the ordered pairs that I care about? As you think about that, Alistair has a good point, which is why I think von Neumann probably liked this way of updating things better. For one, I only have 4 neighbors, so it's simpler. But these diagonal values seem to be less close, right? So these are geometrically square root of 2. You could also say by something like what's called the taxicab metric, they're 2 steps away, right? You don't share an edge with the central square. So it seems weird to let these count as much as the things that are directly adjacent. That's a great observation. So go and you get the chance to do our practice exercises for this chapter, which I love. And one of the things that we do is we diffuse. So we treat a diffusion process of particles as if it's an automaton spreading out with cells of a board. And when we do that, you want most of the cells to go to these, and then you're going to allow some of them to go to the diagonal. So that's a way of getting in between Moore and von Neumann. So think of that when you do it. The other thing I would say is you could also go and make a honeycomb of hexagons. So in that particular case, everybody is the same distance. You have 6 neighbors, and they're going to be all equally distant from a central square. And that's a kind of a cool way of representing it. And our engine is not going to implement that, so that would be a great project for you. You can go and make some cool hexagonal 6-neighbor automaton. In the meantime, we probably can answer where our row and column values need to be. We know we're going to have these in the same order. So these elements need to be presented in the same order, but then we're going to squeeze in, right, each of these diagonal elements. And this is going to be 1 row previous and 1 column previous. So this is R minus 1, C minus 1. This is R minus 1, C plus 1. This is R plus 1, C plus 1. And this is R plus 1, C minus 1. So when we go back to functions, I'm close. I call this neighbor cells. I'm close to being able to have the same thing. It's not a bad idea for me to just put them in like that. But how I'm going to represent them is, let's first do R minus 1, C minus 1. That's my northwest element. Then this was my north. And so then I need northeast. And all of these are in R minus 1. So then we go R minus 1, C plus 1. So I'm going to view it as this way. And now we're going down to east. So that's RC plus 1. And now I need to go southeast. So that's R plus 1, C plus 1. And then we go to south, which is R plus 1C. And then we need to go to southwest. So southwest is going to be R plus 1, C minus 1. And then we go back up to the west cell, which is R, and then the previous column of C minus 1. And I just wrote it in this way so that you could see, this is across the top. Then we go down, and then we go along the bottom, going right to left. And then we have the western element. It's one of the most potentially annoying bugs to get, right? Because I have to present it in some order. And at the end of the day, I need to type this out. So in this particular case, it's a little annoying, but we're done. And all that, now the reason why I split out that step is that so now in either case, regardless of the neighborhood type, range through the neighboring cells and add them to the neighborhood. And here's the benefit of representing the state of the cell as a string, because I can just say, well, for the current cell in the neighbor cells. And what's nice about that is I can just type X comma Y. Thank you, Python, for giving me something easy. And it's going to say for X, Y, and neighbor cells, that's going to give me the X value and the Y value in the tuple. Great. Because all I then have to do is to say that the neighborhood needs to have concatenated to the end of it whatever the current cell that I'm looking at is. But that was the benefit of saying, if the first one is R minus 1C, well, just go in and access that cell. So that's current board of X and Y. And it's that easy. What did I miss? I missed something. We can't do what happened last time where I look like a huge embarrassment in front of my own mother. And it's because one of you knew what I had done wrong and you all ignored it and then watched me fail. Because they are strings. Yeah, that's the benefit of representing all the cells as strings. Yeah, thank you, Remy. Are you on the board? Are you on the board? So this was all really well and good, except I need to be worried, right? We're at the bottom of the function hierarchy. We're in the subroutine that's actually doing the work. And because that's the case, we need to make sure that it actually is on the board. So let's not get ahead of ourselves. We need to check that the cell is indeed on the board. Okay. But fortunately, that's easy. So if, for example, and we can look at one of our patterns, I don't know. I don't have a lot of big boards, but for the arpentomino or something, say that this is the entire board. You're in this corner cell. When you look at its neighbors, you're going to get all these cells up here, and they're not on the board. So you don't want to be accessing board of that. That would be a really bad thing. So instead, what I'll do is I'm going to say, is it the case that we're on the board? So is in field of current board X and Y, is that the case? And if so, then I'm going to add it. But then I should say, well, hang on. Then does this mean I'm going to have an incomplete neighborhood? So now I've got the opposite problem. If it's not on the board, that's bad because we want the neighborhood to have the appropriate number of elements. And one thing we could do is we could handle all these edge cases. Oh my God, what a nightmare that's going to be. And so we don't want to do that. What we actually want to do is just have an else statement. And I'm going to move this here. And in this else statement, I'm just going to do something very simple, which is to assume that everybody off the board is dead. Okay, well, that's mean, but it has the default state. So we're going to say neighborhood in this case is going to plus equal whatever our default state is going to be, which I've said we're just kind of assuming is a 0. And then our function is done and we're good to go. Of course, I need to write in field, but in field's the exact same function that we had before. It takes a two-dimensional list of something, takes an I and a j. It checks if it's off the board. So is the row or column index too small? Is it too big? In any of those cases, return false. If I survive all those checks, return true. And we've written our neighborhood to string function. And now all of a sudden, as if by magic, when we look at our code, it's all done. Is it possible that we've written the engine for an arbitrary cellular automaton that could have as many states as we wanted and have a rule set that's as exotic as we possibly might imagine? And it's just finished. It's hardly any longer than what we had with Game of Life, right? It's just a little over 200 lines of code. And so the engine is finished, and we're basically ready to run this on like any automaton that we might possibly imagine, except we need to do a little bit of work. So one of the things that we need to do the input output. So we need to be able to read in a board. We also need to be able to read in a rule set. So if you look at rules, as I said, don't get terrified. We've got a bunch of boards for you. We've got a bunch of rules for you. And we need to be able to read in just anything. But all the rules have the same structure. So, you know, if it's a more neighborhood, it's got elements of length 9, colon, and then the update cell. If it's something like Langton loop, we have 5 elements and then a colon and then whatever the updated cell state is. So the other thing that's nice is with reading in a board, I'll show you this automaton. You can click on whatever you like, and this is the exact same file format that we had before when we looked at Game of Life, except I had zeros and ones before, and now you can have other elements here. And so when we look at our drawing function, or excuse me, custom IO, I'm going to tell you that I went ahead and I gave you read board from file, because if you look at this and you compare it against Game of Life, the approach is the exact same. I'm going to read in the entire file. I'm going to convert it into a bunch of lines. I'm going to call a subroutine that's going to range over a given row and take all the elements in that row and convert them. And in this particular case, I don't have to convert anything, because I'm going to read in each element of a row as a string. And that's what I want. So remember, the board is a two-dimensional list of strings. And so this is going to, these functions were very comparable, even a little bit easier to what we had with the Game of Life. However, what I haven't done, and I could give to you, but I think it's a little bit of practicing writing parsing code, is reading the rules from file. So we've got our rule set, and our rule set is like Game of Life rules, or our rule set is like Langton's loop, and we want to be able to read that from file. Now, in both cases, you might say, oh no, we've got to handle the two cases as different. But actually, no, because both cases are, you have a string, you separated by with another single element string by a colon, and you have a bunch of lines representing that exact same circumstance. So whether you have 5 elements before the colon or 9, everything else is the same. So when we look at io.py, to implement this function, we just need to kind of refresh our memory about how we parse things in. And I'll go through this pretty quickly, because the first thing that we're going to do is I'm going to declare a collection of rules that are going to map neighborhoods to updated states. And it's going to start off as empty. And way down here, that's what I'm going to return. So that's what I want to produce from the file. And now we want to open the file and convert it to a giant string. And so we had our block that says with open. And in this case, the argument that it takes is a file name. It's going to return this dictionary mapping strings, which are neighborhoods, to strings, which are states. And I will say open file name in read mode as a file. And so now this file is an object with a variable name equal to file. And once I do that, I'm going to say giant string is equal to what happens when I say file.read. So that reads in the entire contents of the file, puts them in a giant string, and when this block finishes, the file is closed because I don't need it anymore. And now I'll do things like parsing it, like saying, well, the trimmed version of that is what happens when I say giant string dot strip. This gets rid of leading and trailing white space. Then we say, I'm going to convert this thing into a bunch of strings. So I'll say the lines of the file are what's equal to trimmed string dot split lines. And after I've split those lines, now, lines is a list of strings, one for each line. So now that I know that, I'm just going to say range over all the lines and parse them. Okay. And as I do this, I'm going to say for whatever the current line is, ranging over the list of strings that I'm calling lines, now I need to parse this line. And I could pass that to a subroutine. This is going to be really short, so I'm not even going to bother doing that. I'm going to say, what is the current line? So if I look at the current line, and I look at Game of Life rules, the current line is a string representing the neighborhood, a colon, and another element representing the updated cell's state. So for that reason, to parse the line, I just need to split it at the colon. And I know how to do that. So I can split something at a comma, which is what we saw last time. And now I'm going to split it at a colon. This is a slightly different format. This is why we didn't import CSV when we worked with Game of Life, just as a little aside. And I could have represented this as a CSV as well, but maybe I didn't. And so I'm going to say that there are two parts of the line corresponding to splitting it at the colon. And when I do that, I'm going to say, I hope that there are only two things. So this will give me a list of strings, which is everything up to the colon and everything past it. If that's not equal to 2, I'm going to say a value error. Someone has been putting too many or too few colons in my file. Okay, that would be bad. Otherwise, I have just two things, and the first thing is the neighborhood string, so that's parts of 0. And the second thing I care about is the new state, and that's parts of 1. And now at this point in time, I'm just going to say, okay, add it to the dictionary, and I'm going to say rules of neighborhood string equal new state. Why? Because it maps the neighborhood string, which is what's before the colon, to whatever the new state is that this cell gets, which is what's after the colon. And then, of course, we return this rule dictionary. Pretty good. I'll take a pause because BZ has a great question. And you didn't ask it of me last time, so I'm disappointed because that was really the time, like, the statute of limitations has expired for this question, but I'm going to honor it because we do the same thing when I read board from file. This is going to be down here. This is the same thing we did with Game of Life. When we read the board from file, the first thing we do is we open the file, we convert it to a giant string, and then we work with that giant string. And your question is, and it's a good one, well, why is it that that's okay? In other words, when I look at my read rules from file function, I've got this line that says giant string is equal to what happens when I read the file and convert it to a string. And then I work with it. So why are you worried? What would you be concerned about? I mean, I share your concern. Is that, and I agree, this should give you an error. I mean, this is like, Python is just not a serious person. And this is an example of it. In an effort to sort of protect you and protect all of our like delicate sensibilities, Python is saying, I'm fine with this. This is okay. Most languages would get very angry right now and say that giant string has not been declared because giant string is declared inside of this block. And in most languages, that would mean its life is confined only to this block. In the same way that if I call a function on a variable, that variable only lives inside of the function. That's a good thing. So the scope of that variable only lives inside of its, like the block, the highest level block that it's contained within. And when you declare a variable like this in a lot of languages, that's the case. So you get an error here, and for good reason. Python says, you know what? I don't mind. That can create some really weird problems if you declare a variable inside of a block and it's really nested. Another great point for why you shouldn't deeply nest things, because you could wind up deeply nesting something and then realizing, well, I'm naming a variable the same thing, but yeah, it's way out here. Why would it think it's the same thing? But Python's like, no, it's the same thing. If you define something way deep inside of a block, you have access to it well outside of the block. That's kind of unserious, but it's useful in this case. And I left this in the hope, in the fervent prayer that somebody would point that out and allow me to criticize Python for it. So now I get to do it, which makes me happy. So thank you. Now, we also need to parse the colors. So one thing that we have not talked about is the correspondence of what I color each cell. And for example, I'll show you Game of Life. All right, this is simple. Game of Life is going to say state 0 is going to be dark gray. State 1 is going to be white. Langton is going to have 9 different states. In the original formulation, I think they had 8, and it's because state 8 was the same as state 0, but then your animation looks really weird because you can't differentiate between something that's black and something that's dark gray. And you might actually want to. So these are all background cells for the most part. And it's like everything that's useful in terms of our replicator is going to be 1 through 8. So that's why they get away with this and say it's an 8-state automaton. But then there's other things. Here's one that actually has 11. So this is why we use strings, because you go from 0 up to 9. And then I'm going to say, oh, we're going to use A to be green. And we have to reuse some of the same colors here. But in this particular case, how you see these files work is that it's the same representation. You have the state type and then the colon and then the color. So that function, as a result, as long as you understand this is going to be very similar, I'm not going to type it out. It is just going to be boring because we've just done something like this. So it's a very similar type of function where it ranges through, makes a big string, makes our dictionary, and then takes the first part, and it also gets rid of any trailing space. I probably should have done the same thing, but it reads in the state, which is before the colon, and then it reads in the color, which is what's after the colon, and it creates this map. All good. So we've got this. At the end of the day, it's going to represent, and I should say it's a dictionary of strings to strings. So it's the same thing. So it'll map like state 2 to the color purple. So that's it for parsing. I don't have anything else in custom.io.py to write. And I need to do a little bit of drawing. But for this, I have drawing code for the Game of Life. And when we looked at the Game of Life, we had a high-level function called draw game boards that took an alive color and a dead color, took a cell width and the scaling factor that we multiply the radius of each cell by. And it ranges over and it passes most of that to a subroutine to draw a single board. And when we drew the single board, you remember how this works. We create the dimensions of the surface object that we're going to draw upon, and then we're going to fill everything with the dead color, and then we're going to range over the board, and we're going to create a circle, and it's going to have the appropriate position and radius, and then we're going to color it with the live color if it's alive. So that was if it was alive. I'll just point you to, in our automaton code, everything here is done because the draw game boards is not going to take an alive color and a dead color. It's still going to take the boards. It's still going to take my cell width. It's still going to take the colors, but it's going to take them as a mapping of the states to the color names. And then I'm going to have a scaling factor too. It's still going to return a list of surfaces. So everything here is the same. Exact same. When we draw a board, it's a little different, but it's so tedious. Like, we're going to create our surface having the appropriate size. So far, so good. I'm going to say, here are my colors. Okay, and here is where, this is a different map. So this is a different map that maps names of colors to their RGB representations. We worked with dark gray last time. We know it's 60, 60, 60. We know that white is the maximal amount of R, G, and B. Black is 0, 0, 0 because it's the absence of light. And then we have different colors here that I picked to try and have a nice palette and also match it up against the Langton loop's original color scheme from the 80s. You could change these if you like, but this maps color names to the color tuples that we have. So we're going to set the background color to dark gray, which is, I should say, not necessarily to dark gray, but it's the color for state 0. And then I'm going to have the radius gets multiplied by the scaling factor that I have. And then I range over the board. I make sure that the current thing is in the current state is in the color map as a key. And then as long as it's not equal to 0, then I'm going to color in the circle. So everything here is the exact same. I set the center of the circle, X and Y values, and I draw the circle with the appropriate radius. The only thing that changes here is I add the color map value associated with the color that I care about. So that is that much more generality than what we've already seen. I just have a couple of maps here that I'm using to represent the fact that I'm going from two colors that I'm going to give as input to potentially 2 colors, potentially 40 colors, right? And everything's going to get mapped there. So by far the engine is more enjoyable. And what I want to do is take the opportunity to actually run everything, because I can read everything that I need in from file. I can run my simulation, and then I can visualize it. And I also have some code in animate.py, which is identical to what we had before, which will allow me to take a list of these Pygame surface objects and convert them to an MP4 and make a pretty video. So let's do that. Let's go into main. And as I said, processing command line arguments is not the most fun. We don't want to have a 4-hour code along, or I don't at least. And so we're going to have a check to make sure that if there are fewer than 7 command line arguments, that would be bad. This is friendly to the user, so it tells the user exactly how we should be running this. So we're going to take the neighborhood type, von Neumann or more. That's a string, and so sys.argv is just a list of strings, so we just say whatever the first element is von Neumann or more. The rule file is going to say where the strings are found, and I could go ahead and start checking these parameters. The functions are going to do that too, but I don't want to clog main too much, but it would be good practice to make sure that these values are good. Here's where the rule strings are going to be found, so that's where my mapping comes from. Here's the initial board that I want to run this on. Here's where I want to write it to. Here's how many pixels wide each cell should be. And here's how many generations to play the automaton. And then there's one extra, which is that I have a default, so this is a default color map that maps states to colors. And it sort of assumes that you have at most 9 states. So I probably should make that a little bit better. But I'm never going to use this code because I'm always going to pass in a color map file that I have. So we're going to get to say there is a final color map that I'm always going to plug in as an 8th parameter. And that says, where is it that I can go in and access this color map that's going to map states to their colors, and read that in from file using that function I just showed you in custom.io.py. And that's going to give you this map. So that's read in successfully if you make it there. And you'll get a message to the user. So again, I could process these and make sure that all of these parameters are valid. But in the meantime, I'm just going to say, we're going to say command line arguments read. And once the command line arguments are read at this point in time, all I need to do is run the simulation. So the first thing I want to do is read in the board from file. Okay. And the other thing I'll need to do is read in the rules. So I think I have the rules first. I have the rules first, and then I have the board. So let's first reading in rules from file. And so I'm going to say the rules are equal to read rules from file, and I've got a bunch of imports up here for you where I've already curated exactly what functions you're going to need from each file. So this, I can see the code in different files because I've got these imports. In particular, I've got read rules from file and color map and board from file imported up here. So I can assume that those functions are there. And if I want to read the rules from file, well, what did I call this? I called this the rule file. So I need to say rule file, and that's it. Okay. And I'll say, let's give a thumbs up to the user. So I'll say rules read, and now reading in board from file. And I'll say that the board, so the initial board that I need to work with, is equal to read board from file. And I'm going to read in my initial board file. I think that's what I called it. Yeah. So I've taken that from the user, and now I'll say board read. And I don't want to read in the color map yet because I want to play the automaton. So simulating the automaton, boards is going to be a list of game boards corresponding to playing the automaton using my initial board, using my number of generations, and that's another parameter that I took in from the user and converted to an integer, and then using my neighborhood type and using the rules that I've read in from file. So you might say, how did I know how to do that? Well, it's because that's the order in the functions. Initial board, number of generations, neighborhood type, and rules. So when I look at main, I have my initial at board, number of generations, neighborhood type, and rules. So at this point in time, I'll say game played or automaton simulated. And if I simulate the automaton, what do I want to do it? I want to draw it to file. Or I should say to canvas. Okay, and so that's our next step, which is to say, let's initiate Pygame, initialize it. Way down here, I'm going to quit it. To run this, you're going to need to pip install Pygame, as well as in animate, we need NumPy, and we need image IO, and we need that image IO with the extra FFmpeg string associated with it. But if you followed Game of Life, we've already imported all of that. So in the meantime, I'll say we initialize Pygame. Here's where we're going to say surfaces is equal to draw the game boards. So this is going to give us all of our canvases that we care about. I need to give it the boards. That's the result of the simulation. I need to give it the cell width, which is how many pixels wide to draw each cell. And I need to give it the color map. I could also give it the scaling factor, but I'm not going to. I don't need to do that. So I need the boards, I need the cell width, and I need the color map. The scaling factor can just get automatically set to its default value of 0.8. And at this point in time, I'm going to print and say boards drawn. And now we get to do the fun thing, which is to say animate the automaton and produce a movie. So the video path that I care about is whatever the output file was plus .mp4. It's still just a string. And I want to call from animate.py, I'm calling animate surfaces, and I'm giving it the surfaces, and I'm giving it the video path. At the end of that, we quit. Again, this animate surfaces comes from animate.py. It takes a list of pygame.surface objects. It takes a video path to draw it at, and that's where it puts it. And now we get to run this thing. So what should we do? If we're generalizing the game of life into an arbitrary automaton, unfortunately, we probably should do the most boring thing first, which is to make sure that it still works on the game of life. So if we open up a terminal, I don't know what I've done here. Okay. If we open up a terminal and I'm in Python src and I'm going to navigate into Cellular Automata. Once there, here's where I need to be careful. And I need to look to say, what is it I really want to do? I need to run Python 3 or Python if I'm on a Windows machine. Then main.py. That's the file I'm running. It's got def main in it. And then what else? Well, the neighborhood type. Game of life is a more neighborhood. Where are my rule strings found? Well, let's look. They're in rules, and they're in /gol rules.txt. What is my starting game board file name? In that particular case, I'm going to say it's in boards / what do I want to do? Let's do the Gosper gun. I always like the Gosper gun. So say boards / Gosper _ gun.csv. And then the next thing is the output file. So that's going to go to output / Gosper gun. It adds the MP4 automatically for me. And then the cell width is next. So let's make it 20 wide. The number of generations should be, I don't know, let's do 100. Seems reasonable. I don't need to see a big simulation. I just want to see some of this. And then the color map. I don't actually need to give it anything. Let's be precise because I've got a game of life color map. And the color map is going to say color maps / game of life.txt. So I've given all of this. And now I'm ready to run. And you can tell me, do we think it's going to work? How much code have I just written? And especially given that you all tend to withhold things when you know I'm wrong. So what would be our yes versus no on call sheet for this? Is that on call sheet? If so, I need to go gamble on that. Oh, not gamble. Is it going to work? I'm kind of hoping if I say Kalshi enough that people who watch live streams of Kalshi will come over here, or maybe somebody reaches out to me and is like, do you want to do paid promotions for our amazing site? I doubt that's going to happen, but you never know. All right, so I'm going to close my eyes and pray. Oh my goodness, it worked. Okay. So now this thing is running. I'm not running it for too many simulations, so it should be okay. Yeah, Roy Knuth offered $1 for all his mistakes, any typos that you'd find, which is a cool thing. All right, so the animation has finished. Great. And now in the output, I should see something. Yeah, it completed, and it's showing the first step. The dreaded thing that could happen is that it has read in and drawn the first board right, and then either the whole thing goes haywire or the whole screen goes dark. So let's see which of those two things happens. Oh, it works. Oh, it works. So we've got our Gosper gun from before. That's the first proof of concept. We've done something way more powerful than the game of life with basically the same amount of code. I mean, maybe 30% more when you think about processing the color maps and stuff like that. We've hardly done anything more than what we already had done. And here we've got our simulation. So now we get to run the other super fun automata that I told you I like as much or more as the game of life. And let's run the Langton loop. So first off, let's make sure it works. I want to visualize it, so I'm going to have it run for 2 iterations. And I'm going to go back to main and remember what my neighborhood types are going to be. So I'm going to say Python 3 main.py. Neighborhood type is, in this case, is going to be von Neumann. The rule file is going to be rules slash Langton rules, Langton's loop.txt. And then my starting game board file name, which is going to be boards slash Langton loop dot CSV. Where do I draw this thing? Output slash Langton loop. What's the cell width? Let's go 20. We don't want it to be ugly. We can get a faster simulation, but I want it to be somewhat pretty. And then how many generations to run this thing for? I'm going to do 2. And that's just so I can see that it actually is updating. Or I can do 4. All right. And then how many generations do I play this for? How many generations? What's the color map? That's the final thing. So the color map is going to be in color map slash something. And color map's going to be color map slash Langton loop. .txt. Okay. And then we're going to hit enter. Okay. So no such file or directory, rules slash Langton's loop.txt. This is going to be easy to fix. I typed something wrong. Langton loop. Rules slash Langton loop.txt. Okay. All right. So it worked, I think. And we'll see the very start of it. Okay, so that's the very start of it. And now we get to make the whole thing, which is exciting. Let's run the same thing. I'm going to hit the up arrow. And I'm going to run this for a lot more generations. Let's run it for 800 generations so that we can see the full behavior. I'm going to hit run on that. And I'm going to let that go. And that's going to take a few minutes. In the meantime, I'm going to show you some other automata that I pre-made, because running each of these takes a lot of time. The last thing I want to do is run all of those live and have to wait on each one to finish. Now, if I were in another language, if this weren't a Python course, I probably could do it. But Python is slow. And I'm going to say a little about that at the end, because it's not necessarily always, it doesn't have to be slow. There are things we can do to fix it. But for now, I'm going to show you what happens when I take the cake out of the oven. And special thanks to Mia, our TA, who made a bunch of extra rule sets for us and boards for us, so you can play around with this however you like. You can make any kind of different color scheme that you want without having to actually change very much. And I also have I have some of my favorites. So I want to show you some things while this is finishing. All right, first off, I like this one. She made a rock, paper, scissors one. So there's 3 states, and one starts in each corner, and then they sort of like spread to neighbors. And then when they encounter each other, they play rock, paper, scissors with the neighbor. And one of these is rock, one of them's paper, and one of them's scissors. I don't know which one's which. It's a circular thing. But it's actually kind of similar in a weird sense to something that we'll see if you check out my Great Ideas in Computational Biology course, where we talk about this notion that X can beat Y and Y can beat Z, but Z can also beat X. So you get this weird cycle. That kind of pattern is actually happening in a lot of our cells, or all of our cells, all the time. Actually, there are more complicated versions of this looping regulatory system. And we'll talk about that and see something that's even cooler than this. But I like this a lot. Here's one that does crystal growth. This one to me is not quite as thrilling, but it actually comes from a real research paper where they used an automaton to do crystal growth. And if you think this is pretty, we'll do something in part 2 of the course that's far prettier, but this is a cool little starting point. Here is a traffic model using automata that at one point in time was a research paper that got like thousands of citations. So it's hard to, like, we have come along, and this at one point in time, I mean like 30 years ago, not like 100 years ago, but like 30 years ago. This is like a foundational research work in traffic where the points go up. They're trying to go up or right. And as they try to do that, if they encounter each other, they sometimes have to wait. So that's not the most thrilling thing, but the whole point is literally everything that's here is just, our automaton is simulated, so we're getting a drawing in the background, good. But everything that's here is the same engine, but just with different parameters. Predator prey is another one that we have, and this is what you're going to do on the practice exercises for this chapter are inspired by this type of model. In fact, the final picture you're going to get is even cooler. But there are a lot of predator-prey, like two-particle systems, looking at interactions. So here's a system where the prey get to eat the predators, or not the prey get to eat the predators. The predators eat the prey, but the prey can swim away from the predators and propagate. So you start with some clusters of things, and over time you get sort of waves and bands of things. If you like this one, go to our practice exercises on the Gray-Scott model, because the Gray-Scott model is simply amazing and is a way for us to answer the question of how do organisms get patterns of stripes or spots on their skin. Like, it's not as if there's an intelligent painter going through and doing this. And it turns out it can be broken down as essentially an automaton model to explain why this is the case without the presence of any form of intelligence, in the same way that we see patterns emerge here. And then there's Langton's ant. So Langton's ant is an ant that makes very simple decisions. It's also named after Chris Langton, who did the Langton loops. How it works is you start an ant, which is shown here in red, and the ant is going to change color, and the color only represents which direction the ant is traveling. So at every point in time, the ant moves. It determines, it checks what is the color of the square it's on. So it asks, am I on a white square or am I on a black square? And if I'm on a white square, I turn 90 degrees clockwise. I change the color of the cell that I'm on from white to black, and then I move forward. If I'm on a black square, I turn 90 degrees counter or anti-clockwise. I change the color to white, and I move forward. So as a result, the ant is shown here as the colored dot. And it winds up being this perhaps not very predictable pattern. And you might wonder, what on earth is going to happen as the ant continues walking? I like this as much as Game of Life, because the answer to that question is not obvious at all. What looks like is happening currently is that it's following, let's use a fancy term from the class. Let's call this path pseudo-random, because it's not random. It's taking a series of steps that I told you it always takes one of two actions based off of whether it sees a white cell or a black cell. And yet when you animate this, it looks like it's a random path. This was at one point in time a fascinating one, because you have this pseudo-random behavior that emerges from deterministic rules. And yet when we expand this out over a huge number of generations and we speed it up, which is what I'm going to do now, you see that eventually what happens, and we need a bigger board to really see this. It looks like Go tiles or something, doesn't it? But when you speed this up, after like 10,000 generations of it seeming to look like it's not doing anything, it eventually hits a point that we're going to see soon. where it does something that's not random. And I don't have a good, simple explanation of why that's the case. But do you see how it started to loop? So it's gone off the screen and we ran it for longer than we needed to. But it hits this point where the ant has followed what seemed like a random path. And then eventually it hits a point where it actually, after 10,000 steps, it repeats the same pattern of about 100 steps and just rotates off into infinity. So what would cause it to have this seemingly random behavior and then all of a sudden very non-random behavior? Bizarre thing to observe in a system that's so simple. And if you want to run that or change the colors or do whatever you like, run it for more steps and see that on a bigger board, you're welcome to do it. In the meantime, our main event, which is that the Langton loops have finished and we can take a look at them. So in our output, we have Langton loops. And these Langton loops are going to run for a minute 20. And here's my favorite cellular automaton. And I hope you're going to get to see why. So we don't need the terminal anymore. I can make this bigger. Make it even a little bigger over here. And I'll hit play. I'm going to have a sip of water first. All right. Now, with no further ado, let's hit play. So what we see is an arm gets extended, it makes two 90-degree turns left, and then it closes off the loop. So as a result, you started with one of these cells, and I'm calling these loops cells. I think that's a reasonable thing to do. And they're made up of smaller cells in terms of what we think of as cells in a cellular automaton. So we have like different layers here of abstraction. And then we went to 2, and now we have 4. And now we're about to have 8, and so on. So at every point in time, the arm extends for a period of time, makes 3 left turns, and then when it closes off, it stops the cycle, but then the cells are able to expand on this parameter in different areas. What's amazing about it, though, is a couple of things. So, number one, eventually, when it doesn't have any additional stimulus, I guess, from the outside or from other cells, and that happens here, the cell enters like a stasis or a death state. So this collection of cells is always going to be in this particular orientation. So we have not only self-replication, but we have a death state too. That's, to me, what makes it really cool. Also, look at how much these look like biological structures. They design them to almost be like, you have a double helix structure of DNA with information that's protected, or you have, a cellular membrane with information that's protected. And so all these cells look amazingly biological in one respect, but this was a landmark achievement in demonstrating a simple system for self-replication. Von Neumann tried to do this in the 50s. It was why he invented cellular automata, essentially, was to try and study self-replication. And he was not able to come up with something that was even close to this beautiful. He had a self-replicator. I've never even actually seen it because it had something like a few dozen states, and it had millions of cells. So our initial cell is just this, whereas von Neumann's was enormous. So this has the nice simplicity in that I think it was Edgar Codd was able to reduce the number of states, but he had hundreds of millions of cells. And so you had this very complicated thing. The beauty of Langton's approach is that you get the self-replication, but you also have only 8 states, and you have a small initial collection of a few dozen cells. So that's really cool. And I've not seen a simpler version of this. I don't think you could really greatly improve this to get that many fewer cells in your starting point and still get self-replication. So you may have seen Conway's Game of Life. This is my favorite automaton. If you want to go study other automata, you can just go and make the rule sets for them. And you can do other sorts of things too, like, I don't know, change the colors, play around with this, do whatever you like. Post all that stuff on our Discord. We'd love to see it. In the meantime, we're ready for some practice exercises. So we're completing the chapter now, but you can go and answer a question like, which it actually was addressed by Alan Turing a long time ago, which is, why do zebras have stripes? Why do leopards have spots? What process in the skin of these organisms, which is non-intelligent, is able to produce beautiful patterns from what must be simple rules, which is very closely related to cellular automata, and it turns out that the answer can be addressed with automaton-like things. So you can go and do that. The other point I would make is our simulations weren't the fastest, were they? And part of the reason why is that the Python list that's built into Python is and always has been very slow. Fortunately, Python is going to have another language come along and hold its hand, and we're going to have a much better way or faster way of representing two-dimensional lists if that's what we want to have. We'll see that probably soon. More importantly, we're going to start making a transition to object-oriented programming, where we've done really some, I think, pretty sophisticated things for an introductory programming course. But to start doing really complex things, I need to move up a layer of abstraction and be able to treat certain things in code as objects. And these objects will have attributes, they'll be able to interact with each other. And that's going to allow us to have like the next power of abstraction. So yeah, that's where programming is going to shift and allow us to do something really complex. But it turns out that everything that we could possibly imagine to do at the same time can also be represented with a very simple machine that Alan Turing came up with nearly 100 years ago. And so we're going to talk about that side of things too, as well as what actually goes on inside of the computer. Because at the end of the day, the computer is literally just a bunch of switches. So how is it that we're able to do such astounding things in computing these days with a machine that's just a bunch of ones and zeros? If that sounds interesting, it's because it is, and you get to see it in the rest of the course. But all that is for another time. So I will see you then, and until that time, like, subscribe, give us a comment, connect with us on all of our platforms, and of course, happy coding.